Hi there. We have understood the various operations of matrices, and we have done the addition, subtraction and the multiplication. But when it comes to division, it's not that straightforward because we cannot simply divide the two matrices. We have to find the inverse of the matrix in the denominator, and for that we need to know about the adjoint of the matrix and the determinant of the matrix. And for the determinant we need the transpose of the cofactors of the matrix. So there are a few terms that we need to understand, and these concepts will help us to find out the division of the two matrix, which is not directly possible. So the very first thing we should know in this regard is the transpose of a matrix. As the name goes, we are transporting things here. That is, if we convert the columns into rows, it will become a transpose. Or in other words, if we convert the rows into columns, it will become another transpose. So this is a matrix, and you can see -1, 2 and 5. -1, 2 and 5 now have come in the row, whereas before they were in the column. And the second column now, that is 0, 3 and -1, has become the second row, 0, 3 and -1. So this is how they are different, and B is there, B bar is there, and B basically has this couple of rows, and these couple of rows have become couple of columns. So this is how the transpose is calculated. And you can see that if the general form of a matrix is like this, the transpose of it will be like this. Here you can see A11, A12 and A1n is in the row, but now it becomes the column, that is A11, A12 and A1n. Whereas the final row was AM1, AM2, AMN. Now it has become the final column, AM1, AM2 and AMN. So the general form of a transpose function matrix is like this. We can also write it like this. We just have to place a bar on it, and it will show that we are talking about a matrix in its transposed form. J is the row of jth row of A becomes the jth column, as we have just considered a couple of rows, and we have seen that they have become column. So this is the same thing written in other notations. Now there are rules of transposition, and here if we take the transpose and then another transpose, it will become A. It is simply that if we convert the rows into columns and then again rows into columns, it will be back again in its original form. So this is why it will be equal. Now if we take the sum of two matrices and then take the transpose, it will be equal to the sum of their individual transposes. So this is also holding true. Overall transpose and individual transpose gives us the same value when added. And if alpha is a constant, and multiplying it with A and then taking its transpose will be equal to alpha into A transpose, because A is just alpha is just a constant, can be 3, 4, A, B, C. So you cannot convert a row into column here. It will be simply one element which will be multiplied with all of the members of the matrix. So it is equivalent to writing it like this, where alpha is not having any change due to the transpose. Then we have the product of the two matrices and then its transpose. It will not be equal to the individual transposes of A and B respectively. It will be equal to the product of their individual transposes, but with the order reversed. Here A into B is now B in transpose into A transpose. So there is a difference in the order of the two sides. The order is reversed. So these are some rules of transposition of matrices. These can be verified by considering some numerical example of A and B matrices. Now we have another concept which is known as the determinant of a matrix, which will be helpful in determining the inverse and hence the division of two matrices. So determinant, as the name goes, is going to determine the value of the given matrix. So there will be a single value for the overall matrix. And in this we can write it in either of these two ways. Either we can write det outside the matrix while we are keeping the square brackets, and we can also write it like this, that we place these bars on the symbol and also on the matrix itself. As you can see, instead of the square brackets, now we are writing the bars. So here we are, how we write the determinant. Now comes the matter of how we can find the value. It is simply the cross multiplication if the order is 2 into 2. This is a simple example in which we have 2 into 2 order of the matrix that we want to find the determinant of. And here we have this product of the principal diagonal elements and the secondary diagonal elements. So product of A and D minus product of B and C. The elements in the principal diagonal, their product, and the product of the elements in the secondary diagonal. Again, minus 3 into 2 will be minus 6, and 1 into 1 will be 1. So this is the answer of it, that is minus 7. This is a numerical example of a determinant of 2 into 2 matrix, and this is a symbolic example because the answer is in symbolic terms. Another symbolic example would be this: A11 into A22, here we are, minus A12 into A21, A12 into A21. Now you can find the determinant of a matrix which is written in a modulus sort of sign, just like this. But this matrix is basically of 3 into 3 order, and we are trying to find its determinant as these bars show. The method of calculating the determinant for 3 into 3 is slightly different, and in that is we try to expand the determinant with the help of either one of the rows or with the help of either of all of the columns. That is, we can choose the first row. For example, we can choose any other row. Answer should be the same. So we are choosing the first row. In the first row we have 1. So the row related to 1 and the column related to 1 will be dropped. As you can see, we have dropped the first row and first column because it is related with this element that is in the first row. And in the first row we have then 0. So column related to 0 and row related to 0 will be dropped. And in this row we have minus 4. Here we are, and we will drop the first row and first column here. So after dropping these rows and columns, we have completed the first step, and due to which we have this remaining matrix determinant. This determinant is 2 into 2 order, and here these two couples will make another 2 into 2 order determinant. This one is already written here, and this one is also left, so it is already written here. But we are not going to just write them separately. We will add and subtract them with the consecutive alternative signs. The first term will have positive sign, second one will be having a negative sign, and the third one will be having positive sign. And if there is a fourth one, it will have a negative sign again. So alternative signs are used, and behind that there is the logic of cofactors, and there is a certain formula that determines these signs that we will see soon. But for this example, very simple numerical example, we are trying to keep it as simple and numeric as possible. But in addition to these alternative signs, we are also using the row that we used for expansion. This was 1 in the first row, so that 1 is written because this 1 gave rise to this determinant. Then there was 0, so this 0 is written because this gave rise to this determinant. And then we have minus 4 here, and this is the related subdeterminant. So we can call these subdeterminants that are a part of the overall determinant. So now we can solve these because we already know the method of solving a 2 into 2 determinant, and here we have done this. So solving this numerically will give us the answer, which is 5 in this case. So this is the general form of 3 into 3 determinant, and this is how we will solve this. You can pause the video and see that this will be the result of the expansion of these determinants that we solved here in a sequential way. So this was about the finding of a determinant of a matrix and also the transpose of a matrix. Here we have A and B, and we found those transposes and also saw the rules of transposition. So this was about transpose and determinant of the matrices. Now we will consider the cofactors and minors of a matrix.